Okay, so this video is going to be about the heat equation again, but this time in 2 dimensions. And in particular, we're going to be looking at the steady state temperature. That is using the Laplace equation, but what that means is in 2 dimensions the heat equation looks like this, but the steady state temperature is when the temperature doesn't change with respect to time. So what you end up having is what I have over here. This notation is just an operator. It means the second derivative with respect to x and y of the temperature function. Okay, so what we're going to be looking for here is the temperature function, which is here I'm calling it u, and it's a function of x and y. So what we have here is a 2-dimensional plate. Right here I had it laid face down. As you can see here, oh, I forgot to cite where this came from. It came from Wikipedia. Anyway, as you can see on this picture here, it's well insulated. The temperatures along the edges are constant. Along this edge, the temperature is 0. Along this edge, the temperature is 0, and along that edge, the temperature is 0. And what we're going to do is we're going to imagine that we heat up this edge. Okay, so we hold a lighter to it or something like that, and then we wait a while. So then we let the heat be distributed throughout this plate. And what we want to do is we want to see what the temperature distribution looks like sometime t later, once it's reached a steady state. Okay, so hopefully this video won't take too long. Actually, in the 1D video, I sort of skipped over the separation of variables part of this. So in this video, I wanted to kind of cover that quickly, but it takes a long time. So I'm hoping that this video is not too long. So okay, so anyway, let's get started. So with separation of variables, what you do is you assume that the solution takes this form. Okay, so it's the product of a function just of x and a function of y. So when you plug this into the Laplace equation, you take the second derivative with respect to x, and you add that to the second derivative with respect to y. So you end up with this. Okay, and so from now on, I'm just gonna have like x double prime, y double prime, and x. I'm gonna leave out the brackets here. Okay, so what can we do with this? What we want to do with the separation of variables, the whole point is to transform the partial differential equation into something that's easier to work with, like ordinary differential equations. So what we end up doing here is we end up forming 2 ODEs. Okay, so since this is a function of x and this is a function of y, this second order equation here is separable. So what we end up having is this. Okay, so since this is a function of x and this is a function of y, then if you hold y constant and you vary x, then this function here would vary as well, but it can't, because if these two things are equivalent, if we hold y constant, this thing can vary. So conversely, if you hold x constant, you vary y, this thing varies, but it can't because this is being held constant. So there's something here called a separation constant. So from this, our two ordinary differential equations are this. Okay, so these are 2 second order linear homogeneous ordinary differential equations. They're easy to solve. So what we want to do is find the characteristic equation of each one. I'm going to call this equation 1, call this equation 2. So as you can, sorry, I should have pointed this out. So these are our boundary conditions up here, and you can see that for these 2 boundary conditions, we have y equals to 2 and y equals 0. So because of that, I'm going to look at this second equation. I'm going to apply those boundary conditions to this sort of as like initial conditions. So it's going to help us. Find a solution for y for this second equation number 2 here. Okay. And I should also mention that I'm going to plot the solution in MATLAB like I always do. So I really don't want this video to be too long, so I'm going to try to hurry up here. Okay, so how do you solve this? Oh god. This is supposed to be y. Okay. Okay, so how do you solve this? We look at the characteristic equation, and we find out that the roots of the characteristic equation, which I'm calling lambda, equal this. So then you can look at each case. You can look at when this constant equals 0. You can look at when this constant is positive, and then what you end up finding is that like these this constant is not 0 and it's not positive. Actually, it turns out that this constant is negative. That means that lambda is complex. So when the characteristic equation has these roots, that means that we have some sines and cosines. Okay, so now is when we have to introduce these boundary conditions. So we have when y is 0, our function equals 0, and y equals 2, our function equals 0. So when you plug in those boundary conditions into this, you find out that when you have y equals 0, you have 0 here, so this term here goes to 1. Sine of 0 goes to 0, so you have a equals 0. Our other boundary condition is that when y equals 2, so a is 0, so I'm not going to write the cosine, you have the sine of 2 equals 0. Okay, so we don't want b equals 0 because that would be a trivial solution, so we don't want this. But when does the sine of something equal 0? The sine of something here equals 0 when this part here equals some constant multiple of pi. So that means that we've just solved this part of our trial solution here. Okay, so now we have this. So now we want to look at this guy here. Okay, so from equation 1, we have what do we say this constant was when we divide by 2 and square both sides? So when we find the roots of the characteristic equation of this ODE, we have, which leads us to, okay, so when the roots of the characteristic equation of the second order homogeneous ODE are like this, we know that the solution has this form. Okay, and then when we look at our other boundary condition, it's here that when x is 0, then the function equals 0. So that means, plug in 0 here, and what do we get? We get this. So we have a relationship between c and d, which tells us this. Sorry this is taking so long, but we're almost there. I'm trying to go quick. What does this look like here? It looks like the hyperbolic cosine function. So if I divide this by 2, right, multiply that by 2, that's fine because this is just a constant. So when I multiply this by 2, I just have another constant, right? Let's call it c with a little hat on top. What this ends up equaling is some constant times the hyperbolic cosine. Okay, so we're almost there. Okay, so now we have x and we have y. Okay, there's y, there's x. So we said that our trial solution was like this. Okay, so now when I plug in x and y here, we have this. Okay, so I multiplied the constants together, so this new constant here is just the product of those other two constants, so it's just a constant. No big deal. Okay, so now, what else can we do with this? Well, n takes all these values, we mentioned that. So since the Laplace equation is linear, that means that the principle of superposition is can be used here, so what this means is that we can add up all the individual solutions corresponding to each value of n here. Almost here. So you know what's coming next. We're going to need the Fourier series for this constant here. So we're going to need our last boundary condition. So when x is 2, we have 25. So here I'm going to say, I should point out too that this is the solution. I didn't circle the solution in my last video. Now we're trying to find this constant here. Okay, so I plugged in 2 for x here. So what's this here? This doesn't have a variable in it, so this is just a number here. So I'm going to divide both sides by the hyperbolic cosine function here, and you can see that what's left over is the Fourier sine series of this guy here. Okay, so when we have the Fourier sine series like this, we know that we can solve for b sub n by using an integral. And since the length of y goes from 0 to 2, we have this guy here. Okay, almost done. So I'm not going to do this integral here. I'll just write down what the solution is. So the solutions to this correspond to when n is an odd number. Okay, so we're almost there. So this leaves us with our final solution with all of our constants found, which is this. Okay, so here's our final solution. This is what we've been looking for. So now I'm going to open up MATLAB and plot this solution. Okay, so here we are in MATLAB. This is all the stuff I did before. Okay, so we're going to set x from 0 to 2. We're going to set y to from 0 to 2 because those are the dimensions of the plate. Next I'm going to use mesh grid to create my mesh of x and y. Now this is my function u. Similar to what I did in the last video, I can't input an infinite series here, or at least if you can, I don't know how to do it in MATLAB. So instead what I did was I set n equal to 1, 3, 5, 7, all the way up to, I think, up to 27. So I got a bunch of terms here. So it's as you're going to see, or along the edge that's being heated, the 25-degree edge. It's not going to be perfect. It's going to be a little bit wavy, but it's going to be better than my last video, that's for sure. And then I'll show you what happens when you use a smaller number of terms here. I'll do that after. Okay, so I just run the mesh function, and this is what you end up with. So this is the plate. This is the x-axis here. This is the y-axis. You go from 0 to 2. So you heat this side up to 25 degrees, and you can see how the heat is distributed over time once it's reached a steady state. Let me show you this in 3D here. Okay, so this is what I was talking about here. That's the edge. Let me just turn it this way. That's the edge that we heated. So remember, along this edge, our temperature function is equal to 25. But the way that I represented 25 was with an infinite Fourier series. So if I was able to use an infinite series, you would see that this edge right here would be completely smooth. It would come up here to 25, go across along 25, and then come back down. But it's not smooth because I wasn't able to use the entire infinite Fourier series. I only used, I think, I don't know, 10 or 20 terms or something like that. So let me show you what happens if you use even less. And you have like a fewer number of terms you have, the worse your representation is. Okay, so compared to an infinite series, my 10 or 20 terms here is terrible. But they can get worse, so let me show you what happens when you only use, let's say, one term. Okay, if you remember what the Fourier series is, from 0 to 2, this function equals 25, and I'm representing by using sine. So from like half a period of sine looks like this. So you can see that it's not a very good representation. But the more terms you use, the better it gets. So if I use 2 terms, it's still terrible. But as you'll see, it's a little bit better. So the more terms I use, and the more modes I have, then the better my representation is. And like I said, when I use 20-something terms, my representation gets a lot better. Okay, so thank you very much for watching, and I'll talk to you later.